talk is completely a different thing now. It's about diagnostic of electrophysiological signals. So we do diagnostic on biosignals. So this is about medicine. What we basically have is we built in the past years, we built software packages that can analyze brainwave signals and cardiology signals. And we kind of vendor sell our own software, or we do also a joint venture with Unique Medical and do programming with them. And today I will show you what we did in terms of deep learning. So these are all the deep learning projects that we built in the past years, and I will go through them step by step. But I think first it's a good idea to give you an introduction into what are electrical biosignals anyway. So it's really a very specialized topic, I think, in deep learning. So what we have is the body, and what we kind of get of the signals are, for example, muscle signals. And for another source of electrical biosignals would be EKG, so the electrical signal of the heart, of the ventricles. And also other type of signal, which is our main focus, are brainwave signals. So these are called EEG, so electroencephalographic signals. And you can measure that by electrodes and have a time series of data in the end. And what we do is basically analyze this time series of data and do then deep learning and diagnostic with that signals. The electrical biosignal in the brainwave is captured by a differential amplifier. So you have one or several electrodes glued on the top of the head or even implanted into the head. You have a very sensitive differential amplifier. This was already done in 1992, 1999 by Hans Berger. So it's a quite old technology. And you get a time series signal, as you see here below. What you also can do is you can measure on the wrist and on the chest to get the signal, electrical signal of the heart, and you will get basically these QRS complexes, which are the heartbeats. And you also can use that for diagnostic. And we will use also that signal for diagnostic with deep learning. So let's have a closer look in the EKG. So what you have is basically a three-wave signal. You have the ventricles, they have electrical activity. When the blood is rushing in the top, so you have this P wave. Then you have the most important, the QRS complex is the ventricle, which strokes out the blood. And then you have a repolarization. So we have a three-phase signal, basically, and you have a time wave which repeats all the time. Most importantly, you have normal heartbeats, and they are also irregular and pathologic heartbeats, which is used for diagnostic of pathologies. This is an example of abnormal heartbeat. In the top, you see here some weird strokes that are between, so you not have really very regular heartbeats, but they're kind of irregular. And one of the most severe cases is the atrial fibrillation. So that's a kind of very irregular heartbeat, and the ventricle is not really working. And one of our projects was, for example, to detect these irregular heartbeats from this time series data. Yeah, there's a kind of a prevalence in the world. 1% of the world suffers from that. 9% over 80 years suffer from that. And there's an Austrian number of that too. Not so important, I think. Another very important signal what we care about is the electroencephalogram. So this is about pyramid cells in the brain. So we have electrical activity that goes through the scalp, and you can measure there with a very sensitive amplifier. So you have this excitatory postsynaptic potential that gives you kind of peaks. So you always have some peaks and troughs in this time series data. So this data is very complex. It's hard to analyze. You have a lot of sources in this brain, and you have a lot of sensors that measure that. So it's really one of the most complex signals what you can get in the world, I think. This is a real-world example of how this look like. So the x-axis is the time, and then you have several sensors coming from this cap and from this measurement amplifier, and you get a very complex signal, and you want to analyze that. And you do this for a very long time. For example, this is 15 seconds. This is not very long, but you can do this up to 5 days or even 1 month. And you get a lot of pages of data that you have to visually analyze it. So now the current gold standard is to visually trade and mark patterns in this time series data. And yeah, this is basically time-consuming, confusing, and quite boring, I think. These are some examples. So this would be, for example, this is a epileptic seizure. You have to get life support in 3 minutes. This is a very normal signal. This is just sleep. And the next one even looks like very close. So it's, if the eyes are closed, you had to get a kind of a background rhythm. This is very normal. That's okay. The next example is already a focal seizure from an epileptic patient. It's kind of a different signal what you get. So the irregularity is much higher. You have a rhythmic activity. So they call this kind of rhythmic pattern. And this builds up the epileptic seizure. The next example here, this is very important. That's epileptic spike, a temporal spike. It's very short in duration. It's only milliseconds long. But if you have that, you already could have epilepsy, and you will need surgical intervention or medication treatment. The next example is just eating. So we also have a lot of artifacts that you get. So that's very normal, even if it looks very severe like the first example. And then there's kind of if you wake up, and then if you are in the status epilepticus. So short message is this is a very complex signal to analyze. There are some basic problems we want to solve. For example, seizure detection, differentiate in a classification problems, normal EEG to a seizure EEG in a long-term recording. This is a very important example for us for diagnostic, is to find these very short time epileptic spikes. So this is one example. This is not temporal, so you might not have epilepsy, but it's already you have to mark that in the recording. That's also very important to find that. So this is only 15 or to 20 seconds what you see here. If you have a full week of recording, you can imagine how hard is it to find these events and to do a diagnostic based on that. So if you find something like this, you get medication for 5 years or a surgical intervention. If you don't find it, you don't. So you see, it's very important, and it's really time consuming, and it's really tough for people to do that. This is another example from the ICU where you have a status epilepticus. That is quite clear if you see the picture. Then you also can get these electrical brainwave signals from neonates. You have a few sensors only because the skull is so small. You only have to place 2 to up to 6 or 8 electrodes on the skull. Some people now also do 21, and you get a completely different signal. And I will show you a project about that. And then you can pull up the whole body with signals if you want, like in this polysomnographic sleep staging, where this patient is undergoing a observed sleep state to see if the sleep is okay or if it is pathologic. So what we want to do with AI in this project, we want to analyze the signals to get a diagnosis, to help to diagnose all these signals and with these signals. So to decide if you have epilepsy or not, do you need anti-seizure medication or not? Is there atrial fibrillation? Is there a stroke? Do you need hospitalization of the patient? I need to change the treatment? So this is what we want to do. So let's go to all these projects, what we did in the past. So the first is about cardiology. This is about this electrical signal of the heart, EKG. What we did is we analyzed this local recording systems. We had a portable recording system for EKG. We analyzed this waveform by a very old algorithm already published in some years ago, which is kind of the basic what everyone does to get these peaks of this heart signal. And then we did the deep learning classification to classify the sequence of this data as normal or abnormal. So if you look into this data in the time series, you already see a kind of representation. You see that this is abnormal behavior here because these intervals are not very regular, they are very irregular. So there's a chance that you analyze that to classify this sequence as normal or abnormal. And this is how we did it. So we used these sequence numbers here. So all numbers are sequence distances between one heartbeat to the next. And then we used bidirectional GRU-based sequence analyzer to analyze the sequence and to classify the sequence in several stages. Then upon that, we built an attention network to really focus on where is the most important part of this pathologic sequence, and then we did a classification with that to get in the end pathologic or not. We compared these numbers or this classification with a naive algorithm, so just one labeling by one reviewer, and already were able to, with this project, to outperform this naive algorithm by a quite a large margin. So this was a quite success for starter. We also decided to do even go further to do a recurrent time series analysis by an autoencoder. So autoencoder gives you information about the structure of the data, so what lies behind this data. It's not really giving you a graph, but it's more giving you a latent vector to encode these features. And we did that with this time sequences of the heartbeats. So we trained the autoencoder in the first phase, then we are freezing the encoding part, and then with these encoded features, we do a classification. And this is also possible to do that, to classify it. So it's just another way to do it, basically. Autoencoding has the disadvantage that it's not very stable if the input is fluctuating a lot. So nowadays it's a lot used in machine learning applications in industry, where they have a lot of parts that have the same visual representation, and there is where the autoencoder is very strong. And if you encode this latent vector in a lot of features and overlay it with red, with the actual waveform, you see how many features and what part of the signal is learned from these signals. So it gives you a kind of explainability, but it's very poor, I think. Yeah, this was the first project. This was about cardiology. So we're coming now to the main focus. It's about spike detection, the detection of the small epileptic discharges. First, we asked ourselves, what kind of problem is this? So how to approach all this? So is it image classification, which is not, I think it's not even a localization, it's more object detection with several classes, because you have a lot of data, you have a lot of this different type of the spikes. So there are different types even of the spikes in this signal. So it's an object detection problem. So we converted all this data in a kind of object detection problem and solved it in a kind of image analyzing way. The first approach, what we did was very simple. We did a sensitive kind of threshold detector and then learned a deep neural network to classify one event a spike or not. You can do it as before, just extracting the features now in a different way. We have this input matrix of data, so it's very structured data. We compress it to a one-channel information feature map. And then we analyze it as before with a sequence analyzer. So the time sequence is retained. We analyze the time sequence, do attention on that, and see where is the most important part of the input, that is an epileptic spike or not. If you look at these attention maps, that's very interesting. You get a kind of a presentation. Where is the spike? Where is it coming from? So I plotted here one example, true positive, false positive, true negative, and the false negative example. And you can kind of see the explainability, where is the wrong or the good decision is coming from. The problem with this approach is this pre-detector. So it might be even too complex. So we decided after a while, because the performance was not sufficient, to do it end-to-end, so really to train an end-to-end network. For that, we used the approach of the regional CNN image classification. We use the same structure, so we kind of feed as the picture is going in the bottom side here, feeds in, and whereas the image is segmented and there's a region proposal and we classify the regions. We did this with the EG picture, basically. So we kind of converted it to a picture and used the same structure. And so we segmented all these, we extracted feature, did the region proposal, and we classified as good or bad spike. This is the structure, so the very rough structure. EG comes in, we do a region proposal, alignment with this region proposal, and then we do a detector on these extracted features. and you get a kind of a box plot like you see here on the right side, where it explains what parts are extracted from this signal and what parts are classified. You can look also into the features map. So this is really not good for explainability. Just see there's something happen. You're not really sure what parts are the spikes, what are not. So you not can really, there's no way to describe this deep neural network in that terms. So really looking for a way to explain this a little bit more. So that's not a good idea to look into the feature maps. What we also did is we used an approach to improve the accuracy of the deep regression. So the region proposal has to be very precise. So this event is very short in time. So there's only milliseconds. So we really have to have a precise deep regression. We used this structure from that paper to get a very robust estimation of image parts. So this was used for body pose estimation originally. So there's a kind of very deep network. We used also this Turkey function to improve the accuracy, which was very nice, I think, in the end. And with that, we were able to accurately define the position of the spike besides classification. We also looked into the shift invariance. So the shift invariance in some deep neural networks gives you a problem. If you just move the input data a little bit, you get different classifications. This is really one of the major problems in image classification, object detection. And we found out that we can kind of improve the situation with blur pooling. So that's a paper which was published, I think, I don't know the year yet, but was some time ago, where I can improve this shift invariance. It was in the end, it was not a big problem in our project. So it really depends on the data if you have a shift invariance or not. So in our case, we avoided that because it costs you a lot of processing power to do this blur pooling. So it's a costly operation. We also exploited unsupervised learning. This is a paper from the Google Brain Group. It's unsupervised data augmentation where you put in there's a part that is supervised and there's an unsupervised part. And the unsupervised part is very interesting. You just use unlabeled data, which in medicine you have a lot. You have a lot of unlabeled data, but only a few labeled data sets. So if it's very nice if you use unlabeled data. You put in this unlabeled data set and then you change it a little bit without changing the label. So you're kind of a little bit tweaking this data. And with the tweaked data, you kind of test it if the output of the classification still remains the same. And if this is not the case, you add a loss. And this loss is trained away from the deep neural network. And in the end, you train that the network always puts out the same thing if you tweak the input a little bit. And in our case, what we used to tweak this data was artifact reduction. So we had already an algorithm to reduce or remove signal noise from the signal. And we used that as data augmentation. And this was kind of the key to make this work for EEG. We did also kind of performance testing with that algorithm. So it was interesting because we built this algorithm completely handcrafted in the first place some years ago. And now with this deep learning, you see the improvement is really amazing. You have a lot of improvement in processing time. Depends on if you have a graphic card or you just have a CPU. There's some variants on it. So take-home messages, if you have a CPU, you're really fast in this end-to-end trained model than if you are built this block by block in a software style manner. We did also external validation because in medical applications, it's really important to do a very nice external application validation. So it's not enough to just take a few patients out and test with them. That's normally not working in medicine because you have these patients are very similar. You cannot test in one patient because each patient is very unique. So you really have to go to a different center. This was in a different country, different recording machine, a different set of patients. We tested that and found that we reached 90% sensitivity in this spike classification problem. It was just published this week, so it's brand new. And it outperforms all existing deep learning algorithms and handcrafted algorithms in that area. Yeah, and here's the link to that. And we also integrated this already in our software product. So this is already, you can buy that already online. This CE certification, we're just doing FDA certification for the US market. And this is also very available. Let's go to the next problem. This will be much shorter. This is about neonatal EEG age estimation. So why you want to do that is you want to find out if the baby, when it comes out too early, so it is a neonate, it's some weeks before the official birth date, you want to find out if the brain is developed normally or abnormally. And what you can do is you can read in this EEG data, what you did with this 8 electrode system, and you can kind of correlate the age, the estimate the age to the real age. And if you have a delayed development and the brain is not ready, or you have some problem with the brain development, you will see a kind of deviation from that. So what we did is we built a deep neural network to estimate the brain age. This is a deep regression project done by my colleague Laura. We had a very nice result because if you have a 55-degree line, you basically made it. So the estimated age is as the same age. And if you have a deviation from that, so you have a baby that is really too early, you see a deviation in the estimation. And then you can react on that. So that's the idea. There are a few neurologists out there in the world that can really see that by looking into the data directly, like seeing into the matrix, and to see if the brain is developed correctly or not, but I cannot do it. So I think that's a very tough problem, actually. Next, we looked into sleep staging. So that's a problem with, you have problems with sleep. You want to find out if your sleep stages during the night are good or bad. We built a deep neural network reading in that data and classified into 5 stages. So these are wake, N1, N2, that are sleep stages. Basically, if you are in N2, you sleep very deep. And we compared it to this existing literature, and we had a very nice results here also. So we kind of are at a very good level to do sleep staging also automatically with a deep learning network. It's a very simple network in the end. It's just a convolutional stack and a classification into 5 stages. So even that tough problem that's out there for 20 years, you can solve it with a very simple network. And there's public available data with that. Next, we looked into how could we generate artificial data, because we need a lot of artificial data for training. As I told you, the training data is not very common out there. It's very expensive to label data, medical data. So we looked into one approach that was the multi-style GAN. This, I think, was from NVIDIA group. They had now also a version 2 of that to generate data by GAN. So a generative adversarial network. By just feeding in some noise, you generate some data, and you do this in a multi-scale way because you need a very high resolution, and not this not 4x4 would not be enough for EEG data, because you have a sampling rate from 256 and you have a 10-second window, so you have a lot of samples. You need a very high resolution for doing that. So we built it in a kind of style like this multi-GAN, and the outcome was that. So on the right side, you see this looks like brainwave signals, but it was actually 2 seconds segments of a random seed. So it's really artificial data coming out from a deep neural network that generates brainwaves, and you can use that for improving a discriminator and a classification, or to generate testing data. Yeah, there are a lot of approaches. You can fool neurologists if you're happy with that, but yeah, what we did is, in the end, we used it in a 3-class approach to improve a discriminator. So if you generate a lot of fake data and you want to classify some EEG problem like normal or abnormal, this 3rd class helps you to improve, to stabilize the convergence of the discriminator, which in the end is just a classifier. So you generate a lot of fake data, and that improves training during classification. And you need only a few data sets from original costly data. Yeah, and the new thing what we're working on is EEG diagnosis, basically end-to-end. So what we saw now is kind of supporting the diagnosing by finding something, and then you decide, is this normal, abnormal? What we are now working on in this Eurostars project, CGI, is really to do this end by end. So we want to feed in 20 minutes of EEG data. Then we do a lot of things. Now we're thinking about doing self-supervised learning. We will use the spike detector what we develop. We will develop new epilepsy markers, mostly based on high frequency rippers. Then we do end-to-end training. And what comes out is one number only. So for the whole EEG, you get one number, which is the risk of having epilepsy or not. So this is the goal of the project. So we're just starting up this year. But yeah, I think I'm looking forward to make this happen. So these are some other slides just to give you a short overview what in the market is happening, because every year now there's one startup which beats the other startup, and it's really a fastly growing market, the EEG business, because the EEG business moves really to the home environment. A lot of portable systems coming out, a lot of big companies step in like Philips, the Neuralink from Elon Musk, that was also a joint venture with them. There are a lot of new startup companies. They do EEG helmets, like the C2 helmet on the left side. Philips has this high resolution, 256 sensor array. Then there's Unique Medical. They do this subcutaneous implant data. And we will do the software for the Unique, which is called Episite. So we do also that and do seizure detection there. There are a lot of other companies that coming up, like Brain Scientific. They do a disposable headset even. So normally this costs about 15,000 euros, but you only buy the amplifier box once, and then you have a disposable that you can use, and you don't need to disinfect now. So this is very nice. There's also a linked system that is really a dry electrode system with a Gale pods, the Cerebell. You just put it on in the ICU, and you have a hand monitor. You see if a patient is in status epilepticus or not, and the data is analyzed in the cloud by a deep learning algorithm. So that's very, very nice thing. And there's the company NeuroPace. They do these bone implants to really treat the patients. And they have a lot of patients going on. They have 2,500 patients every year. They have a lot of patient data, and they do deep learning cloud things to really to find the next patient, which looks good to implant the device. You can also find the next parameter for this deep brain stimulation. If there's another patient out there of this 2,500 and it was working out good, you can kind of match the similarity between your brainwaves and these brainwaves to find out what is my stimulation parameter for this device. So that's a very nice idea for medicine, really, to solve this problem for epilepsy. Yeah, there's the Apple Watch that does atrial fibrillation. And interesting thing here is that only the software is CE and FDA certified. So only the software is a medical product, the hardware not. So the hardware is basically just a consumer product. It's also an interesting approach to do that. Yeah, and in the end, what you also can do is you can kind of find out which is the sex of the patient by just doing deep learning. So one guy did just the classification between male and female by just putting in brainwaves. So that's also interesting. In the end, I'm not really sure what you want to do with that, but you see what is possible with deep learning. Yeah, there's no visual representation about male and female, but in the end, it worked with 83% accuracy. Yeah. So this brings me to the end. What we saw today is diagnosis of epilepsy patients with our software, NCVIS and Episite. We can diagnose patients with atrial fibrillation with deep learning, and we can do a lot of testing and status evaluation with sleep, with neonates, and so on. Yeah, this is our group, and this was a podcast recorded by one company in US, and yeah, this is my LinkedIn profile. So this was it from my side.
Cool.
So I think we have time for some questions.